Hello, welcome. In this short video, let us look at some basic examples using the moment method for parameter estimation. So first let us look at the one of the simplest probability distributions, that is Bernoulli distribution. Here the random variable x follows a Bernoulli distribution, the parameter p. So the probability mass function can be written as px of x equal to the parameter p power x multiplied by 1 minus p power 1 minus x. So p is like the probability parameter. So the mean of this random variable is given by the value p. This is from the theory. Now from the sample values, that is given a set of n values or n observations, the sample mean is given by 1 by n summation over I xi. So that is the sample mean, and this is the mean from the theory. Now the moment method basically states that we can equate them and estimate the unknown parameter. So here p becomes the sample mean, that is we can estimate the value of p by using the sample mean, which is nothing but the arithmetic average. Now let us look at the geometric distribution. So here the random variable again follows the geometric distribution with the parameter p. The probability mass function is given by p into 1 minus p power x minus 1. So in this case the parameter is p, so we want to find the value of p. The theory states that the mean value of the random variable x is given by 1 by p, and again of course we have the sample mean. Therefore the estimate of the parameter p from the moment method is given by simply p hat is equal to 1 by the sample mean, which is equal to n by summation over I xi. So that is the estimate of the parameter p using the moment method for geometric distribution. And third one, let us look at the Poisson distribution. Here the random variable follows a Poisson distribution with the parameter lambda. The probability mass function is given by e power minus lambda power x divided by x factorial. Here lambda is always positive, or at least it is always non-negative. So here again the mean value is given by, in theory, lambda. That is, the mean value is the parameter itself, and of course we have the sample mean. So again by moment method the estimate of the parameter lambda is simply the sample mean. Fourth one, the normal distribution, that is the Gaussian distribution. Here we are talking about a continuous random variable, so the probability density function fx of x is given by 1 by square root of 2 pi sigma square exponential of minus of x minus mu whole square divided by 2 sigma square. So that is the normal distribution. This is the probability density function of the random variable x. That means here the x is following a normal distribution with the parameters mu and sigma square. So our goal is to find these two parameters. So in theory the mean value is given by the parameter mu itself, and the variance, that is variance of x, is given by sigma square, and then from samples, that is from observations, the sample mean is given by the arithmetic average, and then the sample variance is given by 1 by n summation over I xi minus x bar whole squared. Therefore by the moment method the estimate of the mean, that is the estimate of the parameter mu, that is mu hat, is equal to x bar, that is the sample mean, and then the estimate of the variance, that is sigma square hat, is given by sample variance. So that is the straightforward implication of the moment method for normal distribution. Finally let us look at the chi-square distribution. It is chi-square distribution with the parameter p. This is chi-square. The probability density function fx of x, the probability density function is given by 1 by gamma of p by 2 into 2 power p by 2 multiplied by x power p by 2 minus 1 e power minus x by 2. Here the theory states that the mean value is given by p, and of course the sample mean is 1 by n summation over I xi. Therefore the parameter p is simply equal to the sample mean. So in this video we have looked at simple examples using the method of moments or moment method for parameter estimation. So first one is Bernoulli distribution. Here the random variable x follows a Bernoulli distribution with the parameter p. So the theory states that the mean value, that is expectation of x, is given by p, and the sample mean is x bar, which is the arithmetic average. So the estimate of the parameter based on the moment method is simply the sample mean. And for the geometric distribution, the probability mass function is slightly different. It is given by p times 1 minus p power x minus 1. And then the mean value of this random variable is 1 by p. So the sample and sample mean, again the arithmetic average. So the parameter estimate of that is p hat is given by 1 by sample mean. That is, its inverse of the sample mean. It is the inverse of the sample mean. And the next one is Poisson distribution. Here the probability mass function is given by e power minus lambda power x by x factorial. Here the sample here the theoretical mean, that is the moment, is given by lambda, that is the expectation of x is lambda. So again the estimate of this parameter lambda is simply the sample mean. And the next one is normal distribution. Here the parameters themselves are basically mean and variance of the distribution. So the parameter estimates based on the moment method are simply mu hat equal to the sample mean, and sigma square hat, that is the estimate of the variance, is given by the sample variance. And finally for chi-square distribution, the parameter p, that is when the probability density function is defined by this expression 1 by gamma of p by 2, 2 power p by 2, x power p by 2 minus 1, and e power minus x by 2. So in this case, it's a special case of gamma distribution, and the mean value in theory, that is based on probability density function, is given by p, and then we have sample mean. So the estimate of p is again the same thing as sample mean, that is p hat is equal to sample mean. Thanks for watching.